Hello, welcome. The purpose of this video is to go through our first key assessment on phase changes and discuss some areas where people maybe got tripped up or didn't perform to the highest level possible and some common trends that I saw in student answers. First off, I'd like to say thank you for watching this video. This kind of reflection is really critical to improvement. Thinking about what you did before and how you can improve is really essential for actually getting better. So even watching this video and putting in that effort is an excellent first step. So thank you for being here. All right, so before we even get into the questions, I'd like to address something here in the academic integrity piece. Notice, you may use your notes, class materials, stuff on the website, Google Classroom, worksheets, anything that you have. So in this assessment, this was asynchronous. There was no time limit. You weren't under any sort of intense pressure here. If you have the opportunity to use your resources, it's probably going to boost your performance if you check your resources. A lot of the stuff that we had in this assessment was really directly related to things that we did in class. So it really does help if you have this option to actually use the resources at your disposal. All right, so let's get into it. The first question was graphing. Lots of people did pretty well on graphing. The most common thing that I saw in graphing, most of us had our graph drawn with a straight edge, which was excellent. Your axes, names, and labels, and a title. For the sake of time, I'm not going to write those out because most people did that pretty well. Most of us plotted our points. I did see a few people who just did not actually plot points. They only showed the line of best fit, so please do make sure you're plotting your points. And then when it came to drawing the line of best fit, some of us did something like this. One single line for the entire graph. So this is not what we're looking for. Your line of best fit should show the pattern for each section of the graph that you see. So you have this increase area, you have this flat area, and then you have another increase. So you actually, in this case, will have several lines of best fit. So hopefully that makes sense now. Number 2 was pretty well done. Any issues I saw here were maybe related to not showing motion and particle arrangement. Both of these are necessary in a particle diagram, but in general, people did pretty well with number 2. All right, number 3, with melting point, most of us identified the melting point, again, by using the graph or the data table. You had a graph with a pattern that might have looked something like this, and most of you were able to say that this flat section, whatever the temperature was at this flat section, is indeed the melting point, which is awesome. The place where people could improve here is where it says explain. So yes, we know, because we've told you, that the flat area of the graph is where a phase change occurs, but in order to fully explain this phenomenon, you have to address how do you know that increasing heat and not seeing a change in temperature means that you have a phase change. So what about this lack of change in temperature gives you indication that it's a phase change? Because the temperature is not increasing, this gives us evidence that the heat energy must be doing something other than making the temperature go up. And indeed, in melting, the heat energy is going into breaking intermolecular forces and separating out particles in a substance. So by seeing a lack of temperature increase, we get some evidence that it's a phase change. So you needed to also address this idea of not only that there's a flat line, but why a flat line means that we have melting, and that is a full explanation. All right. So This next section, I think many of us would have improved our score by carefully reading what the question asked us to do. So the question asked us to explain, we see that word explain again, how heat energy contributes to each section, solid, melting, and liquid. So in my claim, I should be addressing solid, melting, liquid, and heat energy. So in my claim, I should say heat energy does whatever it is that it does in solids. Heat energy does whatever it is that it does in melting, in the phase change. Heat energy does whatever it is that it does in liquids. Well, how do I know what heat energy is doing in each of these sections? Think about this presentation that we had on IMF. And I'm going to point out the slides that might have been helpful here. So remember, we talked about each section individually, liquid, and we talked about boiling in class, but we should know that phase changes happen similarly. So in this case, you're thinking about melting. In class, we discussed boiling. So we know that if you're in one single phase, adding heat energy increases the speed of the particles. This is what's happening as time goes on, as heat is added, as the temperature increases in one single phase. So here I'm just in liquid. Adding heat energy is increasing the speed of the particles. It's not doing anything to IMF. It's not making the particles more spread out. What's happening in this one phase deals with speed of the particles, speed of the particles. And because the particles are moving faster, the temperature increases. Temperature is actually a measure of how fast particles are moving. So faster particles, higher temperature. All right. Adding heat energy increases the speed of the particles. Increasing the speed of the particles means increasing temperature. All right, what about the phase change part? Well, it's not increasing temperature. In the phase change, my particles can't be moving any faster because the temperature is not going up. Temperature is a measure of how fast particles are moving, and so the particles can't move any faster if the temperature is staying the same. So what's going on in the phase change? Well, in the phase change, the particles are spreading out. In the phase change, the particles are spreading out. And more specifically, you'll remember we talked about intermolecular forces. More specifically, they spread out because we break intermolecular forces. We break those connections between the particles. And this is what the heat energy is busy doing. So it's not making particles go faster. It is indeed making the particles spread out, specifically by breaking the intermolecular forces. So heat energy should be making the particles move faster, making the particles spread out, and breaking their IMF. And then with liquid, liquid is of course very similar to solid. It's one single phase. So this is what we're looking for in our claim. In our evidence, this should be straight from your graph. This should be which areas of the graph are relevant to your claim, which areas of your data support your claim. So you're not copying and pasting your graph in here. You're telling me which areas are relevant, which areas support your claim. Your reasoning, well, in your reasoning, you're going to explain exactly what you know, really based on what we learned this day that we talked about IMF, when we talked about patterns and IMF. So in your reasoning, you explain, you answer that why, how do you know, you connect what you see in the graph with what's going on in your claim. So I saw many people talking maybe only about melting here. I also saw a lot of people not address heat energy. You maybe talked about the trends that you saw. You did some sort of CR that was not related to heat energy. It's important to know what the question is asking. This question asks you to discuss heat energy. And so you should be addressing in your claim really specifically what heat energy does. So if you talked about something that was not heat energy, you likely lost points in that section. All right. And then the final section, the comparison with water. I know this one was a little tricky. One thing that tripped up a few people, and I believe that this graph is still incorrect, I did email a new graph for sections A and B. I apologize about that. That was a mistake in sections A and B. Section F, you shouldn't have been affected by that. But the first day we handed out the assignment, there was an incorrect graph, which you unfortunately see here. The correct graph does indeed show the melting. So very similar graph, except we're showing melting, not boiling. So we're comparing the melting of water with the melting of batmanium. One important thing, all control variables were constant: amount of substance, heat source, heat setting, altitude. So some of you were telling me something about different amounts of heat. Both substances received the same amount of heat. They may have differed in temperature. Temperature and heat are not the same thing. That was another common thing I saw. People using heat when they might have meant temperature, not the same thing. And that was something that we mentioned in class. Using those class presentations was going to be really helpful for you here. These two substances did receive the same amount of heat. All right, so this question, identify the areas of both the graphs where the substance is a solid. I saw a lot of people talk about melting in here. You talked about the melting point and why the melting point would be different. Well, that really wasn't what this question was getting at. Melting, of course, would be in part B. So I did need you to show reasoning both for melting and for when we're just in one phase, when we're in a solid. So if you said something about melting, if you were comparing melting points, you weren't really answering the question that was being asked. So first you needed to identify the areas of the graphs. Many of you did that. Some of you missed actually doing that identification, just picking out in the graphs that this is where it's solid. In your batmanium graph, the area in which batmanium was solid, the temperatures at which batmanium was solid. You likely noticed two big differences: the temperature ranges and also the rate of change. The temperature ranges and the rate of change. And then we asked you to explain. So I want you to think about what implications does this have for energy and the different substances. So you really should be comparing the two substances, batmanium and water. So based on the differences you see in temperature and rate of change, what can you say, what can you infer about the two substances? Now, part B, this is where we were asking about melting. This is the part that was asking about melting. So in part B, we were looking for different melting points. You likely saw the melting points were really, really different. You may have also seen that the phase change took different amounts of time. And so again, identifying the areas of the graphs was important. Many of you did that. Some of you did not do this first step. Comparing the graphs, likely these were the areas of comparison, and then explaining. So based on these differences, what can you conclude about water and about batmanium? All right, I hope that helps. If you have further questions, make sure that you have a specific question that I can help you with, and you're welcome to come to office hours, send me an email, whatever works, and thank you for watching.